um, okay, so this is the recitation for Professor Witt's class. Can you hear me in there? Just checking. Okay, thanks. This is the first time I'm doing this, so just bear with me. Thanks. Okay, so this is the recitation, and as you probably know, the homework policy is that homework is really important, but it doesn't really officially count for your grade unless you do poorly in the first exam, in which case you're going to be monitored more closely on whether or not you do the homework, and it just becomes more of a big deal. But in any case, if you do well, then I'm just here to go over the problems again, hopefully explain them a little better, and then what's just in the solutions. And also, I encourage you to come to class with questions and perhaps alternative questions about alternative ways of approaching a problem, and so on and so forth. So, without wasting any more time, let's go straight to it. So, the first two problems on the problem set I think are very easy. So I don't really, and they also have solutions in the back. So unless one of you guys wants me to go over them, I think they're pretty straightforward. So I guess we can move on to the third problem, which is problem 113. Okay. Okay. Problem 113. Okay, so let E and F be mutually exclusive events. In the sample space of an experiment. And suppose, so what does this mean? This literally means that the intersection of the two events is just the null set. And now suppose that the experiment is repeated until either event A or event F occurs. So okay. Okay, what does the sample space of this new super experiment look like? And also, more importantly, show that the probability that event E occurs before event F. So we want to show that probability that E occurs before F is just equal to probability E divided probability E plus probability F. Okay. And we also, let's just denote this as equal to little p, so that we don't need to write this over and over again. Okay. So this problem really illustrates the usefulness of conditional probability, because what we will end up using in this problem will be a simple conditioning argument on the outcome of the first experiment. So let's condition Okay. So there are three things that can happen, right, in the first experiment. It could either result in event E, it could result in event F, or it could result in neither of the two. And those are the only three possibilities, and of course they're disjoint. You can't have two of those three happening at the same time. So we can write the following. Okay, so then P is equal to probability E before F, given that E occurs before F, or that the outcome of the first experiment is E. Let's denote this by E. Plus the probability of E before F, given that, oops, sorry, a little mistake here. Of course, we have to account for this. Times probability E plus probability E before F, given that F occurs, times probability that F occurs, plus, and now if none of these two events happen, or actually before I do that, let's just write this. Before F, given neither E nor F happen, so we can denote this by E or F complement, which means that neither happens, times probability E or F complement. I wonder if I can write on the other boards. Hello? Yeah, I was wondering, can I write on the side of the board, like on the other boards, or is that not visible? Okay. Okay, thanks. Show business. So now we can then rewrite this as that now P is equal to what is probability E before F given that E happens? It's very simple, right? It's just, well, given that E has already occurred, well, it definitely occurred before F. So that's just 1. So we have 1 times probability E. And now what is the probability that E happens before F, given that F happens? Well, that's 0. So it was 0 times probability F. And now, given that neither F nor E happen, that just means that, okay, we just start over, and the probability will just be the same, because we're assuming independent trials also. So times P, and this happens with probability 1 minus PE minus PF. And why can we write this? Well, because the two events are disjoint. So the probability that P or F happens is just equal to the sum of the two probabilities. So therefore, we can write this. And now we can just solve for P here. and we get exactly what we were expecting. So, any questions about this? I think it's a pretty straightforward application of the usefulness of conditional probability. Oh, and this is 112. Oh, I'm sorry. Oops. Okay. This is 112. So if there are no questions, let's move on then. Let's do 113, which is again, it again discusses the the notion of conditional probability. Okay. So here we have a problem with a game of dice. The dice game craps, played as follows. Player throws 2 dice. If the sum is 7 or 11, then she wins. If it's 2, 3, or 12, she loses. If it's anything else, then she continues throwing until she either throws that number again, in which case she wins, or she throws a 7, in which case she loses. So you want to calculate the probability that the player wins. Okay. So we use the same technique. Namely, we condition on outcome of the first roll. And we can very simply write now probability that we win. We can express it as the sum of conditional probabilities, each time weighted by the probability of that particular event on which we're conditioning occurring. So now we're conditioning on the outcome of the first roll. So, well, if we roll 2 dice, we can get anything from 2 to 12, right? So it would be the sum from I equals 2 to 12 of the probability that we win given that we roll I, and of course times the probability that we end up rolling I. Okay? And now what the problem gives us becomes useful. So clearly, probability that we win given that I, when actually is 0, for I equals, because we're told that if the sum is 2, 3, or 12, then we lose. Yeah? Okay, so okay, sure. Okay. Okay, so I have to move. Okay. And now similarly, the probability that we win given I is equal to 1 when I is equal to 7 or 11. Okay. So now in order to calculate the probability of winning, we need to calculate these conditional probabilities for any other possible I. So remember that by problem 112, so when E and F are disjoint, we just calculated the probability that E occurs before F is just probability E divided by probability E plus probability F when E and F are disjoint. Okay. So let's see what happens for I between 3 and 6. Then probability of winning given I is the probability of, what does the problem say? That we throw the number again or that we throw a 7. So this is the probability that we throw I again before 7. So now we can directly apply what we did in problem 112. Because now the two disjoint events are either throwing I or throwing 7. So this is the probability of throwing I divided by probability throwing I plus probability of a 7. Okay. Yeah. Why are we including? Because it is a typo on the solution. You're right. You're absolutely right. From 4 to 6. Thank you. So now let's continue this here. So this probability, I guess after a few calculations, you can see that it is equal to I minus 1 over 5 plus I. And I guess you can do this by just counting the different outcomes of that will give you, I and 7. And now if we were to do this for and 10, we do the same argument. Leads to an I equal to 13 minus I over 19 minus I. So yeah. So now if we were to sum up the whole thing, so this implies that probability of win is somewhere close to 0.5, but slightly less. 4929, blah blah. So this 113. Yeah. So okay. So any questions? Okay. Then let's move on. Okay. Can I erase this? Actually, let me go here. Okay. Okay, so let's do 119, which has a solution in the back of the book, but it's very easy. And it's also instructive about, counting and things like that. So 2 dice are rolled. What is the probability that at least one is a 6? And if the 2 faces are different, what is the probability that at least one is a 6? I did this. Okay. So let's call it the event E, the event at least 1 6. Say D, the event that 2 faces are different. Okay. So now this is a pretty simple problem. First of all, probability of E would just be now, we use the simple counting argument where we just count the number of ways in which we can get at least 1 6 and divide those by the total number of outcomes that can happen. So let's see. Numbers of ways to get E divided by number of total outcomes. Okay. Well, how many ways are there to get at least 1 6? Well, there are 6 ways. No, 11 ways. At least one. Yeah, you can get 2. No. There are 11 ways because it says at least, so we could have 2 6s as well. But do we roll 3 times or we roll 2 times? Number of ways to get. What's the problem? The at least one is a 6. So you could have it be. Oh no, yeah. So you could have it be either the first or the second roll, right? So if you have 2 rolls, one of the 2 has to be a 6. Say if the 6 is here, then you have 6 more options here. But now, say that the 6 is, sorry, this is a little confusing, but say we have 6, then we can have 6 more options here. Now say that the 6 is here, then we would have 6, but we would be overcounting if we considered the case when this guy is a 6 as well. So we have 5. So in total we have 11. So this would be 11, and the total number of outcomes is, of course, 36. It's just 6 times 6. Now the probability that 2 faces are different would just be 1 minus the probability that the two faces are the same, right? They're disjoint events, and they exhaust the whole sample space. So it would be 1 minus, and now in how many ways can this event happen? It can only happen in 6 ways, right? If it's 1, 1, or 2, 2, or 3, 3, 3, 4, 4, and so on and so forth. So we get this, which gives us 5 over 6. And now, so what is the, if the two faces are different, what is the probability that we get at least 1 6? So now we want to calculate the probability of E occurring given that D occurs. Well, again, it's very simple conditional probability. We just write this as the probability of the intersection of the two events divided by the probability of the event that we are conditioning on. And this, and here again we count the outcomes, and I guess we get the probability of E and D. The event two faces are different. Oh, it would just be all the events that we have considered initially, except for the event where we have exactly 2 6s. So we would have 10 events. We divide this by 36. And we already have calculated the probability of D, which is 5 over 6. Oops. 5 over 6. And we do some cancellations. And we get 1 over 3. So, any questions? Fairly straightforward. Okay. So let's do problem 120 now. What did I do with my chalk? Oh. Okay. Oops. Yeah. Okay. So this is in the same spirit, though it is also a little more complicated. Here we have 3 dice that are thrown, and we want to calculate the probability that the same number appears on exactly 2 of the three dice. So thrown. So let's right off the bat say that we have this many outcomes. Now we will partition the sample space in a clever way in order to calculate this probability. So let's say that E is the event that exactly two of 3 numbers are the same. S is the event that all numbers are the same. And D the event that all numbers are different. Same. Yeah. So as we can see, we have partitioned the state space into three mutually disjoint events, and one of these three things has to happen. So we've and they can't happen at the same time, which is what we wanted. And now we want to calculate the probability of E. So if we can calculate the probability of S and the probability of D, we can subtract them from 1 and get the desired result. So, and luckily these two probabilities are not very hard to calculate, because, okay, what is the probability of S? It's the probability that all three numbers are the same. Well, how can that happen? Well, only if you get, 1, 1, 1, or 2, 2, 2, or 3, 3, 3. So it can only happen in 6 possible ways. So we would get 6 over 216. And now let's calculate the probability of D. Well, how can that happen? Well, you have 3 choices. The first one can be anything. It's arbitrary. But the second one has to be different than the first one. So now you have 5 choices instead of 6. And then the third one has to be different from the other 2. So now you have 4 choices. So it would just be 6 times 5 times 4, again divided by 216. So, of course, now we can very easily calculate what it is we want to calculate. So this means that after some calculations, it's 1 minus probability of D, and we get a result of 5 over 12. Okay. So this is equal to 5 over 12. So any questions? Okay. So then let's move on. I'm sorry if these problems are too easy or something, but I guess it's just a review for. I'm sure a lot of you have already seen this stuff before. Okay. Let's do a little more of conditional probability. Okay. So now this is a classic Bayes rule problem. I wouldn't be surprised if Professor Witt did something similar in class. I know I've done it at least 3 times. So you have, suppose that 5% of men and 0.25% of women are colorblind. So let's actually... So let's say that C is the event that a person is colorblind. We don't know, it doesn't have to be a man or a woman or anything. Person is colorblind. And let's say that M is the event that a person is male. So M is male, F is female. And, well, we know that the probability, we're told that 5% of men and 0.25% of women are colorblind. Well, that means that the probability that you are colorblind, given that you are a man, is equal to 5%, which is, yeah. And similarly, the probability that you are colorblind, given that you are a female, is 0.25%. Okay. So now a colorblind person is chosen at random, and we want to calculate the probability that the person is male. Okay. So, oh, and we're also assuming that there's an equal number of male and females, which literally means that probability male equals probability female equals 1/2. Okay. So now we sample this random person, and we want to see if he's colorblind or not. So let's see. We literally want to calculate the probability of someone being colorblind. So, we want to calculate the probability that that given that someone is colorblind, what is the probability that he is a male? So this is a classic application of Bayes' rule. First of all, we write this, we uncondition and write it as the ratio of probability of the intersection over the probability of someone being colorblind. And now, the trick to the problem is to realize that while you don't really know what this probability is, you can use your knowledge of the reverse conditioning to calculate the other probability. Because we know that we can rewrite this now as the probability of colorblind given male times the probability of someone being male. And similarly, we can write probability of someone being colorblind as the sum of the probability of someone being colorblind and male plus the probability of someone being colorblind and female. And then do exactly the same thing that we did in the numerator to these two probabilities in the denominator. So okay. So what is the probability of someone being colorblind given that he's male? Well, it's 0.05 times 1/2. That's the probability that someone is male. And now we do the same thing here. Well, of course, the first one is exactly the same. And the second probability, what is the probability that someone is colorblind given that she is female? Well, it's 0.25%. So how do you write that as a fraction? Yeah, 0.0025, again, times 1/2. And this ends up giving you a pretty high probability. So this is classic Bayes' rule. Any questions? Okay. So now let's do the next problem, which is actually it's a pretty good problem, pretty tricky. So problem 122. So we have two players, A and B, who play until one has two more points than the other. So assuming that each point is independently won by A with probability P, what is the probability that they will play a total of 2n points? And what is the probability that A will win? Okay. So the first observation to make here is that the game can only end after an even number of plays, right? Because someone has to have two more points than the other person. So, it will always be an even number in the end. Like the sum of the two scores will always be an even number. It can be 3-1 or 4-2 or 5-3, but in any case, it's going to be even. So observe, let's write this down. Game and after an even number of plays. Okay. And now, in order for the game to end, say, in 6 plays, what will have had to happen? Well, that would mean that up to game 4, both players would have had to have won 2 games each, and then player A or B would have to win 2 consecutive games right in the end, games 5 and 6. So to put it more abstractly, for the game to end on play 2 times n, players A and B. How do I write this? Well, actually, let me backtrack a little bit, because here I will confuse you. So, since this is happening, a natural way to sort of simplify the problem would be to consider now trials not as the successive games, but rather as a successive series of 2 games, because the game will end after an even number of games. For it to last 2n games, that will mean that for the previous n-1 series of 2 games, sorry, it's confusing, but player A and player B will have to have won 1 game each. So then, at the nth series of 2 games, one of the 2 ends up winning both of them, and the game is over. So let's consider a trial to be a series of 2 games. Okay. Okay. So continued here. So then, for the game to end after 2n plays, this means that the first n-1 trials will have to have resulted in draws. And that the last one ends in a win. The nth one ends with a win. Okay. So what is the probability of drawing? The probability of drawing a trial. Well, that is the probability that either A wins the first game and loses the second game, or it's the probability that B wins the first game and B loses the second game. So this would literally be 2 times P times 1 minus P. And here I'm just abbreviating what I said earlier, because it doesn't matter in which order, of course, this happens. But there are two such events. And let's say, what is the probability that A wins a trial? Well, that would just be P squared, because he would have to win 2 consecutive times. And probability that B wins a trial would just be 1 minus P squared. Okay. Okay. So now we have all the necessary tools to answer the questions that are posed in the problem, because now these trials are independent, which is great because we can just calculate probabilities. Because as you remember, the property of independence is that the probability of something and something else is just the product of the two individual probabilities. Do you have a question? Okay. So probability game ends after 2n trials is the probability that we have n-1 draws and someone wins in the end, and one win in the end. So, and now by independence, yes?
Why do we have two there?
Yes, yeah, sure. Okay, so, we have 2 games in one trial, right? It's a series of 2. And how do you get a draw? You get a draw if, this is game 1. If player A wins game 1 and player B wins game 2. And that happens with probability P times 1 minus P. But you can also draw if the reverse thing happens. So if B wins game 1, so this is game 1 and game 2, and this, of course, it happens with the same probability, right? But of course, this would just be 1 minus P times P. And then you sum those two up. Okay. So now, going back to this probability, this is the the intersection of two events, so we can just calculate the respective probabilities, right? So this is just probability. Let's say that this is event E1, and this is event E2. So this would just be probability of drawing n minus 1 times. They're independent, so we just raise it to the n minus 1 power. And then we want to get one win right in the end, so times probability win. And now we don't care who wins, right? We just want to calculate the probability that the game ends. So it could either end in A's favor or B's favor. It doesn't matter. But we just want to calculate the probability that it ends. So what do we get in the end? We get 2p times 1 minus p, and all of that raised to the n minus first power, times p squared plus 1 minus p squared. So are there any questions? Well, let's answer the second part of the problem, too. Okay, so now what is the probability that A wins? Well, again, we'll do the same old trick by conditioning. What is the probability that A wins given that we play 2n games? Does anyone have an idea? It's very similar to this, but slightly smaller probability, though. Well, it would just be 2p times 1 minus p to the n minus 1 times p squared now, because now we specify who it is we want to win. And we know that player A wins with probability, when it wins the game with probability p. So now, given this information, we know that we can express the probability that A wins as the sum of all these conditional probabilities weighted by the probability of whatever event we are conditioning on occurring. So you can say that this is the infinite sum from n equals 1 to infinity of probability A wins given play 2n games times the probability that we play 2n games. Oops, wait. Yeah, no, yeah, this is right. Wait. I made a small mistake. This is not conditional on. This is the joint probability. This is a big mistake. But yeah, because as we see here, we also we were calculating everything in terms of joint probabilities, not conditional probabilities. So now this makes more sense. And we just get the infinite sum of, let me, so this is just the infinite sum from n equals 1 to infinity of 2p times 1 minus p n minus 1 times p squared. So we take the p squared outside, we get the sum n equals 1 to infinity of and this is just the geometric series, right? 1 minus, just less than 1. Yeah. Geometric series. I'm assuming everyone knows. Yeah.
Could you do this like the same way we did the dice problem? Like, you know the probability that A wins 2 trials and the probability that B wins 2 trials? You're just trying to find the probability that A wins before B. So could you use that same ratio that we did before? The probability of A winning 2 trials over the probability of B winning 2 trials plus the probability of A winning 2 trials?
Yeah, so the question is whether or not we could use the same reasoning as what we did with the dice problem. And off the top of my head, I don't see why one couldn't do it. Because in the end, yeah, we are looking at the probability of A winning before B. But that's in a sense what we're doing here as well. Here we're just taking into account, though, when that actually does happen. So I think if we were to think about it in that way, we'd end up doing exactly the same thing. But it's a valid question. Okay. So I think that's enough with Bayes' rule. I think there's one more problem, but I think that we've exhausted Bayes' rule, beaten it down to a pulp. So why don't we move on to chapter 2? Okay. So, yeah, let's start off with problem 220. So 220 is a classic example of the multinomial distribution. So we have problem 220. So in the multinomial distribution, what we have is we have, say, n independent trials. And each trial results in outcome say, I, where I can range from, say, 0 to some number k, with probability pk. And the multinomial is just a direct generalization of the binomial distribution. So we're interested in calculating what is the probability that, and let's say that x1 is the number of outcome outcome ones, and x2 is the number of outcome that results in 2, and so on and so forth. So probability that x1 is equal to little x1 and x2 is equal to little x2 and k is equal to little xk, then that is just equal to n factorial over x1 factorial, x2 factorial, xk factorial times p1 to the x1, p2 to the x2, pk to the xk power. So this is just the direct generalization of the binomial distribution, where we have the same thing, but this time there are two different. It's like a binary thing, so you only have two different types of outcomes. And now the way to think about how to prove the multinomial theorem, you can directly do it using conditional probability, but that's a little I wouldn't say that it's that hard, but it's just has a lot of algebra in it. But the way you can think about it is that, okay, you want the probability of this event happening, right? So you can literally think about, okay, I have n trials, and I want, out of those trials, I want exactly x1, little x1, to represent outcome 1. And I want exactly little x2 to represent outcome 2, and so on and so forth. So now, so this can happen in a number of ways, right? Depending on the order in which these outcomes happen. So you have the probability that this happens in any order, or in one specific order, I should say, is this probability here, because the trials are independent. But and of course you can jumble everything up in n factorial ways. But you have to take into account that for each one of these blocks of type I events, each one of these can be permuted as well. And if you do not divide by x1 factorial, x2 factorial, up to xk factorial, then you will be severely overcounting the probability. I mean, it probably wouldn't even add up to a probability. It'd be greater than 1. So let me see if I can, yeah. So let's say, let's do just a concrete example. So let's say, say you have 6 trials. Okay. And this happens with probability P1, P2, and P3. Then, say that you have, these, 6 possibilities here. So then, this event could happen, say, if this configuration happened, right? Or it could also happen if, yeah, see, so if this is, but now, yeah, so I think I'm confusing you, but now for each, and of course, we can jumble this up any way we like, right? So which is where the n factorial comes into play. But now, for each one of these blocks of the same numbers, we can permute these as well, right? So, I don't know. I think I'm making a mountain out of a molehill here. But anyway, uh, the moral of the story is that you have to adjust by these factorials. And I can maybe explain it a little better after if someone has a question. Is this a point of difficulty or no? Okay, I'll take that as yeah.
Well, is this something we're supposed to derive, or is this like something that's like supposed to be like a binomial formula, or is it we derive?
It's you don't derive. This is just a formula, but it can be derived by using the binomial sort of distribution arguments. But it's just that you have to write it. So you have to take this whole joint probability, write it as the product of a conditional probability, and then everything else, and keep recursing on that, and you'll see that quite easily you end up with this formula. But I don't think we really have the time. But if someone does want to see a rigorous sort of proof of it, definitely come after recitation or at my office hours also. So, but yeah. So anyway, to go back to this problem, this is a direct application of multinomial because we have a television store owner who figures that 50% of the customers entering the store will purchase an ordinary television set, 20% will purchase a color one, and 30% will be just browsing. So, okay. So let's say T is ordinary TV, C is color, and B is browsing. And this happens with probability P1 equals 1/2, P2 equals 1/5, P3 equals 3/10. Okay? So if 5 TVs if 5 customers enter on any given day, what is the probability that that 2 people purchase a color TV, 2 people get one person gets an ordinary one, and 2 customers get nothing? So, in other words, what is the probability that T is equal to 1, C is equal to 2, and B is equal to 2, given that 5 people, so given that the sum of these 3 things is just equal to 5? Well, we directly apply the multinomial theorem. So this would just be 5 factorial over 1 factorial, 2 factorial, 2 factorial, times 1/2 raised to the first power, so we don't do anything, times 1/5 squared times 3/10 squared. So this just kind of a very easy, straightforward application of the multinomial theorem. Yeah?
Does the conditional part change anything?
Well, okay, so the question was, what is the conditional part? Well, the conditional part, you can basically choose to omit it. It just tells you that, okay, 5 people entered the store. It's probably superfluous to even mention, because when you say 1, 2, and 2, it's directly implied that, okay, 5 people came, because these are the only 3 possibilities. But this just makes it a little more clear, but definitely do not think of this as, the joint probability divided by the probability of the thing you're conditioning on. It's just there for...
So wouldn't that derivation have to be like the probability of all those things given n? Because otherwise you don't know what n is, right?
Yeah, exactly. That derivation, you end up saying, oh, okay, what is the probability that x1 is equal to little x1 given everything else times the probability of everything else.
I'm just saying that that's assuming that x1, x2, that all those numbers fill this space, right? Because otherwise,
Yeah.
it could be possible that like.
Yeah. No, the implicit assumption here is that n is equal to the sum of.
Okay.
If that's not the case, then it's 0.
Okay.
Okay. So I think we can. Let's do problem 232. 232 is just an application of the Poisson approximation to the binomial. So recall that when n is large and p is small, we can approximate a binomial NP distribution by a Poisson with mean n times p, or where this is equal to lambda. So a Poisson random variable with mean n times p. So this is a very useful fact, and this is what we'll use in this problem. Okay, so if you buy a lottery ticket in 50 lotteries, so in our case, n is equal to 50, which is pretty big. P is equal to 1 over 100, which is pretty small. So we can apply this fact. So what is the probability that you will win a prize at least once, exactly once, at least twice? So let's say x is the number of prizes we win in the 50 trials. So we know that x is just binomial n 100, n 1 over 100. But it would be very impractical to try and do anything with this binomial distribution, because the probability that you would have to be summing up, because the binomial is discrete, and you'd have to be just summing up a huge number of probabilities. Say, like, if you wanted to calculate the probability that you're between like 20 wins and 40 wins, you'd have to sum 20 terms of the binomial, which has combinations and factorials, and it would be a mess. So we approximate by x being Poisson, and now n times p is just 1/2. Okay. Oh, and also another difficulty with binomial is that if n is very large, there is no computer that would calculate huge factorials, or at least quickly. So we approximate it, and so then if we were to think of this as a Poisson, probability that x is equal to little k is just e to the minus lambda times lambda to the k over k factorial. And now everything just becomes very easy. So now, what is the probability that we have at least one win? So what is the probability that x is greater than or equal to 1? Well, that is pretty simple. It's just the probability that 1 minus the probability that x is equal to 0, which is 1 minus e to the minus 1/2. Yeah, there are some typos in the solutions. Yeah, it's 1 minus e to the minus 1/2. Yeah. And then what's the probability that we win exactly once? Well, that is just e to the minus 1/2 times 1/2 times 1/2. And what is the probability that we win at least twice? Well, that's just 1 minus the probability that we win 0 times and the probability that we win 1 time, which is 1 minus e to the minus 1/2 minus 1/2 times e to the minus 1/2. So any questions? Pretty easy. Okay. So out of because we're running out of time, out of the next 3 problems, is there one you would like me to do more than the others? Two 243, sure. Do people agree? All right. Yeah, 243 is a good one. It illustrates the use of indicator variables. Okay. So an urn contains n plus m balls, of which n are red and m are black. So balls n red, m black. Let x be the number of red balls removed before the first black ball is chosen. Okay. So I want to determine the expectation of x. Okay. So what is okay. So to do this, we employ this technique, which is very useful, of considering indicator random variables. So consider the random variable xi that is defined to be 0 if actually let's say let's do that. So it's 1 if red ball I is chosen. So now, first of all, yeah, red balls, let's say that they're labeled arbitrarily 1 to n. So we just find a way to differentiate between them. So let's say that xi is 1 if red ball I with label I is chosen before all the black balls, all the blacks. Let's say that this is 0 otherwise. So with this definition, we can see that x, which is the total number of red balls removed before the first black ball is chosen, would just be the sum of these indicator random variables from I equals 1 to n for every single one of these red balls. Okay. And now, okay, so these are equal, so their expectations are going to be equal as well. So this means that the expected value of x is equal to the expected value of the sum I equals 1 to n of xi. Okay, well, expectation is additive, so we can put the expectation into the summation. So this is equal to the sum I equals 1 to n of the expected value xi. Okay. Blah. Okay. So now all that remains to be done is to calculate the expected value of xi. And notice that there's nothing really different about each of the balls, no matter what their label is. So the xi's are IID. They're independent, and or they're identically distributed in any case. We don't need them to be independent, and they're definitely not. But no, they are. But okay, so the expected value of xi is 1 times the probability that xi is equal to 1 plus 0, right? It's either 0 or 1. So it's just equal then to the probability that xi is equal to 1. So this is equal to the probability that red ball I is chosen before all black balls. Okay? Well, this probability is just equal to 1 over n plus 1. Because the reason being is that it's like you have an urn now of m plus 1 balls, and you can pick each one of them with equal probability. So you want to make sure that you pick that in whatever order you pick, I is before all the other black balls. So this would happen with probability 1 over n plus 1 because of the symmetry of the whole situation. Because any other ball could also just so happen that any other ball would be the first to be chosen. But we want the red ball to be that. But they're all equal. They all sum to 1. There are m plus 1 of them. So this is the probability. And of course, this is true for any ball I. It's not there's nothing special about I. So we end up with a very simple result: n over m plus 1. And any questions? Yeah. No, I think we do, yeah, without replacement, yeah.
Probability for first ball is not the same as for the second ball, right?
The first ball,
First big one.
yeah, definitely not. But that's yeah. I mean, that's a very good question, because they're not independent trials. Like whatever happens in the beginning will influence the future. But the whole trick with these indicator random variables is that you sort of get rid of that problem, because you express it in the form of IID random variables in a clever way, where you just consider, you label the balls, and now for each one of these balls, this probability is easily calculated, and these probabilities are independent between one another. What is the probability that you pick red ball I before all the other black balls? Because now you only care about the black balls, and then so. But that is that's a very good point. Because it's all about this probability here, that probability that you pick the red ball I before all the other black balls. Well, in this context, all of the events are equally likely. You could pick, black ball 5 before all the other black balls and red ball I. But you're just interested in picking this one. And because you're restricting yourself to red ball I, it doesn't matter how many red balls remain in the pile, right? In the beginning, you would think, oh, I have n, and then I have m, so it would be n over n plus m or something. But now, since you're restricting yourself to red ball I, this probability just becomes 1 over m plus 1. Okay? Okay, thank you. And thanks for the attendance today. I didn't expect so many people.